Good afternoon, Ghana.
Good afternoon.
All right, let's talk about our final day of class here. Now, my original plan was to talk about right triangles, but as I looked over the curriculum that I have, I thought, you know what? This isn't going to be as good for you as if we do something else. So we're going to talk about right triangles for a little while, but we're going to switch to something a little bit deeper. We're going to talk about centers of triangles. We won't cover my full curriculum on centers of triangles, but first let's talk about a few things about right triangles that probably won't be in your standard curriculum, or at least I want to make sure that you get it. Let's start out with a question. Let's say that you've got a line and a point not on that line. What is the shortest path from that point to the line?
Well, if you were to draw a line through A and draw a line from point C that's perpendicular to A to the line, that would be the shortest path.
Okay, so perhaps that vertical distance right there, we could call that dropping a perpendicular. If we drop that perpendicular, perhaps we have the shortest path, but can you prove it?
You could draw a circle around point A that touches the line.
What would that do?
It would confirm that that was the straightest point, because where the line met the circle, that would be the straightest point that we could use to yeah.
How do you know it meets that line at a tangent point?
I'm not sure.
Let's take a look at this right triangle here that I've drawn. Let's label the legs. And what we know is that a squared plus b squared equals c squared. What do we know about a squared?
That's the base. We know that
a squared is c squared minus b squared.
That's true. Here's what we know about a squared. There's something called the trivial inequality. How many people have heard of that? This is a starting point for a lot of inequalities in mathematics. It says that for a real number, its square is at least 0. And it's only equal to 0 when that real number is 0. That is the only equality case. The square of a negative number is positive and the square of a positive number is positive. Let's start with this inequality. If we add b squared to both sides, then we have a squared plus b squared is at least as large as b squared. Now what can we do?
Could we then say that a squared plus b squared equals c squared?
Yes.
Sorry.
We can make a substitution. A squared plus b squared is c squared, so now we know that c squared is at least as large as b squared. And this tells us that c is at least as large as b. Now, this last part, we've got to make sure we know what we're doing. We're only talking about positive numbers. And with positive numbers, the square root function is monotonically increasing. Do you know what I mean when I say that?
No.
Right here, we know that x plus y is greater than x. And these two things go hand in hand right here. The square root function, if we were to graph the square root of x, it would look like that. It's always going up at least a little bit as it goes to the right. It's half of a parabola. And while we could prove this more rigorously, it's something that we're going to take for granted for the moment. But yeah, the square root function is monotonically increasing. So we can take the square root. And so long as we say, hey, C and B are not the same. In other words, if we have this point up here and we call it X and this point right here and we call it Y, then we know that X and Y are not the same point. There is some positive distance between them because A is not equal to 0. So we remove the equality case, and whenever y is a point that is not on x, that is not exactly the point x, then C is greater than B, so B is the shortest possible distance. Any questions or thoughts about this? Okay.
Could you also use a parallel postulate to prove this?
Now, Norley, can you repeat that?
Could you use a parallel postulate to prove this?
I don't know how. The parallel postulate just would tell us that there's a point through A parallel to line L. So now I'm skipping over a lot of the problem solving curriculum, and I've made the decision to do that because I suspect that you're all going to see that. But we are going to discuss something called Huron's formula. How many of you are familiar with Huron's formula already?
This is the first time I'm hearing of it.
Yes.
Okay, here's what Huron's formula does. Huron's formula helps us find the area of a triangle given its side lengths. And there are some triangles that you can already find the area of relatively simply. If I were to give you, well, we have found the area of equilateral triangles given its side lengths. If I were to give you a triangle like this, and I were to say, hey, this side length down here is 24, this one's 13, this one's 13. We could do that without any special formula. How would we do it?
Well,
I'm not too sure, but with the side lengths being the sides being the same, 13 and 13, it means it's an isosceles triangle.
We have an isosceles.
So the altitude would touch the middle of the base. So then we could solve it like this.
Okay. Right now, what we have are congruent triangles because we have two side lengths and two angles, and that's more than enough. And since those two triangles are congruent, we know that we have equal side lengths down there. So we know that this is 12 and 12 on the two sides. And we have a hypotenuse of 13 for a right triangle. And we quickly find that the height is 5. And so the area is base times height over 2. And we're done. Okay, So with special triangles, equilateral or isosceles, we can find the area pretty easily. There are some triangles, on the other hand, where it's not so easy. And here's an example. We have a triangle with sides of length 13, 14, and 15. Now we know that the area of a triangle is half the base times the height. And we have a base. That's fine. So if we can find any one height of the triangle, then we're fine. So let's draw in that altitude as we've done before. But now what?
Well, we can't assume that it's going towards the middle since there's different side lengths and it's not. So it's not isosceles.
We can use Heron's formula.
Well, we are trying to derive Huron's formula. That's our goal. We're not going to use this blindly. We're going to figure out why it works if it works.
Maybe we could assign variables to each of the side lengths that we currently have. So x, it could be 13 squared minus x squared equals h. Just start.
Okay. What is x?
X would be the base, one of the divided sides of the base.
Okay, let's let D be the foot of the altitude. Let's let AD be x. And let CD be 15 minus x. What can we do now?
Well, we know that the altitude divides the base into two parts with the ratio 13:14. So we know that x would be 13 out of 27 times 15.
Well, let's hold on now. This is not an angle bisector. An angle bisector divides the angle into two equal pieces, and that's not the case in this triangle.
Oh, okay, yeah, I get you.
Could we separate the two triangles and rotate them to get right angle triangles?
Well, we already have right angle triangles in this diagram, don't we? What can we do with those right triangles? Focus on triangle ABD for a moment. What do we know that can help us write an equation?
We know that x squared plus h squared equals 13 squared.
Okay, what else do we know?
It shares a height and base with triangle BDC.
Does share a leg with right triangle BDC? What do we know because of right triangle BDC?
That triangle ADB has a 90-degree angle.
We know it's a right triangle. ABD and CBD both have right angles. They're both right triangles. For one of them, we used the Pythagorean theorem. What about the other one?
We could still use the Pythagorean theorem and then maybe equate both equations to h.
Okay, good. Now here's the thing. You may have been hesitant to do this before now because this doesn't look like most systems of equations that you solved before. It's a little bit more difficult. Now, there's the suggestion that we isolate h squared. I like that idea. That's something that we can do. I'm going to do things just a little bit differently. I'm going to go ahead and expand everything just to get a look at it. Now, it's going to have the same consequence, but I'm just going to subtract. Now, here's the thing. We wanted h, but it's easier to find x. Okay, now what?
Then now we can say 33 over 5 squared plus h squared is equal to 13 squared and find for x.
Good, we can take this and plug it back into one of our equations. The first one is the easier one to do that with. So we plug that in and we have 33 over 5 squared plus b squared equals 13.
Actually, it's h squared.
Sorry, thank you. 33 over 5 squared plus h squared equals 13 squared. Okay, maybe that's a little bit of a pain, but it's not that big of a deal. I'm going to go ahead and fast forward us with a little bit of arithmetic here. We multiply 169 times 25. Let's see, that's 4225 over 25. Then I'm going to subtract out the 1089 over 25. And that gives us 3136 over 25. And what is the square root of that? It's going to be between 50 and 60. We can do a little estimation to get us close. What is 55 squared?
$3,025.
Very good. Looks like it might be about 56, and we square that and we find it does work. So our height is 56 over 5. And now we can use our formula to find the area. Base times height over 2 is equal to 15 times 56 over 5 divided by 2, and we get 84 as the area. Luckily, we turned out to have a nice area. That usually doesn't happen. The 13, 14, 15 triangle is special. It's the first triangle after the 3, 4, 5 where we have 3 consecutive integer side lengths and an integer area. The next one's much, much bigger. So let's talk about what we did here. What did we do? Somebody walk through the steps and just verbalize what we did. Try to say it in 2 or 3 sentences.
Well, we basically used simultaneous equations to solve for H. First with the left side triangle ADB and BDC by showing the equations that we could form using the information we already had. And then we expanded. We know x squared plus h squared is already in the equation. 169 brought it to the other side and subtracted, and we'll switch the 30x minus 225. So when we bring 225 to the other side to add to the 27 with 198, and we solved for x first before attempting to solve for h. And since we had x, we then put x into the equation and then subtracted it from 13 squared times 25 times 25 to get our h being the square root 56/5.
Okay, that's probably more words than we need. I'm just going to say it more simply. We knew that we needed an altitude, so we dropped an altitude, created, and then we had a system of 2 equations from application of the Pythagorean theorem, and we solved that system of equations. And so if you can put it into words, and you know, your words were fine, that was fine. If you can put something into words, you may be able to generalize the process. So let's see if we can generalize this process. Now, let's draw any old triangle. And let's call the side lengths A, B, and C. And forgive how bad my drawing is. We can even find the area of a triangle when we draw badly, given the side lengths. Okay, we're calling them A, B, and C, as general as it gets. And we're going to draw an altitude. We're going to call it H. And then we're going to split the base into X and B minus X. And we know that the area of this triangle is base times height divided by 2. And we want this, you know, perhaps in terms of things that are, I'll call it natural to the diagram, A, B, and C. So we want to see if we can find H and replace H in that formula. So we look at our right triangles and we say, okay, x squared plus h squared equals a squared. And then b minus x squared plus h squared equals c squared. What can we do with this system of equations? And I know this looks like a lot. There are 5 variables here. This looks intimidating. But we know that A, B, and C are parameters. We're just going to relax and work with them, just as we did in the example problem. What can we do first?
We can expand like we did with the previous one.
Okay. And now we could say one of 2 things. Either we could subtract equations, or we could say, hey, let's substitute with the first equation into the second. And we get the same result. I'm mostly just showing that we could think of it in a different way. So now we have minus 2bx plus a squared plus b squared equals c squared. Do I have that right?
Yep.
Okay, so let's isolate x. Somebody tell me, what is x when all the dust settles?
Well, first, x equals c squared minus a squared minus b squared over minus 2b.
Okay, that's true. So x equals a squared plus b squared minus c squared over 2b. Wow, that looks more complicated than before.
Mr. Crawford, please, isn't it minus b squared?
I'm sorry, say again?
Your x is equal to a squared plus b squared. I'm saying, isn't it minus b squared?
I think a squared and b squared have the same sign.
Oh, okay. Yeah.
So before we had x, and x was just a simple number, and then we plugged it in back into the first equation. Here, are we going to plug that into x squared plus h squared equals a squared? I guess we're going to have to. That looks really scary. Oh, wow. That's the equation we have to work with. Okay, this is a point in time. If you have never done algebra that looks this nasty, I'm going to say this. Look for a strategy, right? Don't try to chew this off all at once. Let's not square out that big nasty term, a squared plus b squared minus c squared over 2b. Let's try to find some strategy that allows us to handle this without quite such a headache. So here's the thing, we want h. So let's isolate h. Now, what do we have on the right-hand side here?
We have a squared minus a squared plus b squared minus c squared.
I'm going to stop you. I'm going to stop you. That's too complicated. Right? That's the point here, is we have all this complicated looking stuff. Describe it in some structural way. What's nice about the right-hand side? We know
I think that there are 2a squared.
Well, remember, we're going to square that second term and subtract it off from a squared. What if we say it like this? It's a squared minus a bunch of junk squared. What do we have?
A Pythagorean triple.
Maybe, but let's not assume that. We don't know if we're dealing with integers or not. what we have is a difference of squares. What can we do with the difference of squares?
We could cancel out the common factors.
Maybe. What can we do with any difference of squares?
Square root.
Maybe. We could certainly throw a square root on both sides, but I'd rather save the complicated stuff till the end, if possible. What can we do with the difference of squares? Think back to your algebra. If I said x squared minus y squared, what could you do with that?
I could break it down into x minus y times x plus y.
Yes, you can factor it into a sum and a difference. We can rewrite this as a plus a squared plus b squared minus c squared over 2b, and a minus a squared plus b squared minus c squared all over 2b. Okay, that looks a little less scary. Why does it look less scary?
It gives us less work to do.
Yeah, we're not squaring the big nasty part. That definitely looks less scary to me. Okay, what can we do now?
We try and simplify our fraction.
What do you mean by simplify?
Well, we know there's something that's in common between the denominator and the numerator b. So maybe if we divide both by b, a squared plus b minus c over 2.
I think you're getting warm, and maybe you're saying it but not quite saying it right. What if we just made one fraction in each factor? Just find a common denominator and rewrite it. Rewriting things is one of your best friends in algebra. If you're not sure what to do, ask yourself, can I rewrite this in a way that might be more useful? And our first factor becomes 2ab plus a squared plus b squared minus c squared over 2b. And our second factor becomes 2ab minus a squared minus b squared plus c squared all over 2b. Now let's focus on the first factor for a moment. Does anybody notice anything interesting about this first factor?
Yes. You can
divide it by 2b.
Sorry, was that David speaking first?
Yes. I was gonna say you could cancel 2b with 2ab, but now I think that wouldn't be correct.
Yeah, that would just be undoing what we just did.
Yeah.
What do we notice that's interesting in the numerator?
B is a part of it as well as 2. So it shares common factors with the denominator.
Now there's B.
Can we factorize it?
Okay, think factoring. What factors? Look at that piece right there. What do you see?
we can break it down we can find
Complete the square.
Is there a difference of 2 squares?
Yes, it is, non-Orly.
And I think it should be a plus b squared.
Great observation. What about in the second square? It's a little bit tougher to see. Sorry, the second factor. What do we see in the numerator there? Does that help?
Yeah, it would be bracket A plus B times A minus B.
Not quite.
Sorry, A minus B squared. Yeah.
Okay, yeah, we're gonna have C squared minus A minus B squared all over 2B. Okay. We've made real progress. Let's remember, this is all H squared. We've made substantial progress, and what we have is fantastic. I mean, look back a few lines at what we started with. We were going to have to square stuff that already had square terms. We were going to get stuff with a to the 4th power and b to the 4th power and all kinds of crazy terms in there. But by focusing on the structure of the algebra, by organizing things in the nicest possible way, we now have 2 instances of differences of squares, and we can factor these. We have a plus b plus c and a plus b minus c in the first factor, still all over 2b. And in the second factor, we have c plus a minus b, and then c minus a minus b, which is c minus a plus b, all over 2b. Wow. Okay, I'm going to rewrite this, but now is the time I'm going to take the square root. What's going to happen when I take the square root?
To be
You'll be left with a plus b plus c.
Okay, what are we going to have in the denominator? When I take that square root,
still going to be 2b.
it's still going to be 2b. Well, that's kind of nice. And then in the numerator, we're just going to have all these factors. I'm going to write them like this: a plus b plus c, then a plus b minus c, a minus b plus c, and minus a plus b plus c. That part is going to be underneath a square root. So now let's remember, we want the area. And I'm going to represent the area with capital K. This is a traditional variable that is often used to represent the area of a triangle. If you ever read old math books or old math papers, you might see this capital K. And that area is base times height divided by 2. And we have H now. So what we have is B times, I'm just going to say all this mess under the square root divided by 2 times 2b. Now what happens? What's in both the numerator and the denominator?
B.
B. Okay, that just canceled. Well, that's nice. Now, I don't like fractions. Fractions are the ugliest thing in mathematics. So we could write this as a formula now. We could say that's good enough for us. But here's what we're going to do. We're going to find a way to get rid of the fractions. We're going to introduce a new variable. Maybe a couple of new variables. First, let's say the perimeter is a plus b plus c, right? That's simple enough, the sum of the side lengths of the original triangle. But really, in order to get rid of the fractions, we're going to say that's equal to 2 times the semi-perimeter. So it's 2s. So here is what we've got so far. We've got the area of the triangle equals the square root of a plus b plus c, a plus b minus c, a minus b plus c, and minus a plus b plus c, all over 4. And if we replace a plus b plus c with 2 times the semi-perimeter, we get 2s. And then how do we describe a plus b minus c? If a plus b plus c is 2s, what is a plus b minus c?
Would that be S or 2S minus C?
You're close. It's 2s minus 2c. Similarly, a minus b plus c is 2s minus 2b, and minus a plus b plus c is 2s minus 2a. What happens now?
I think we can factor out 2s.
Not 2s. What can we factor out?
2.
We can factor a 2 out of each one of those factors under the square root. So that's 2 to the 4th power. What is the square root of 2 to the 4th power?
2 squared, which is 4.
Exactly. And that's just going to cancel out with the denominator. And when all is said and done, under the radical, we get s. I'm going to reorder the terms. S minus a, s minus b, and s minus c. And that gives us a formula for the area of a triangle, just in terms of its sides and nothing else.
Mr. Crawford, what did you say S was again?
S is the semi-perimeter. It's half the perimeter.
Half the perimeter.
That's right. And let's make sure this works. Let's try this for this triangle up here. Somebody tell me, what is the semi-perimeter of a 13, 14, 15 triangle?
16.
21. 21.
Okay, we get 21 as the semi-perimeter.
20.
13 plus 14 plus 15 is 42. Okay, so now let's plug in the square root of the semi-perimeter. Semi-perimeter minus A, we'll call A 13, B 14, and C 15. S minus A times S minus B times S minus C. And then let's organize factors. We've got 3 times 7 times 2 cubed times another 7 times a 2 and a 3. So we have the square root of 2 to the 4th, 3 squared, and 7 squared. And that's equal to 2 squared times 3 times 7. And what is that?
84.
The same thing that we got before by going through all that algebra. So let's take a review. Base times height divided by 2. But the height is not part of the original information, and we look for a way to relate it to A, B, and C. So we take these, we introduce a new variable, x, helps divide the base into 2, and then we have a system of equations. And we solve for x, we isolate x, we plug it back into one of those equations, and then we do a big strategic algebraic dance. We use the difference of squares to rewrite what we're looking at, and then we reorganize the terms. We package some of them into squares themselves, and that allows us to once again use the difference of squares to get a bunch of factors that happen to look a lot like each other. And then we say, well, that's not good enough because we want something without fractions. So we substitute A plus B plus C equals 2S. And then it's just a matter of pulling out factors until we have our formula. This is Huron's formula. Any questions or thoughts about this?
Mr. Crawford, I was wondering, so when we were driving all these formulas, how would you want to go about if you were to derive it by ourselves? What would you say we should remember just in case we had to derive it by ourselves? Like we didn't just remember it off the top of our heads.
Yeah, absolutely.
It's a lot.
Yeah, it feels like a lot. It feels like a lot. Just, remember the reasons we did things. If you can, try to see things together. Like, this right here. If you see that much algebra, maybe you just have to do it. The older you get, the more experience you have, the more algebra you'll be able to handle. You'll be practiced with it. But it's always good to look at the structure of the algebra that you're looking at and say, okay, I've got squares. Can I factor this in any way? We're always looking for ways to factor things in algebra. And we're dealing with a bunch of squares. And you know what? Monday in class, we did a difference of squares to help us find Pythagorean triples. So, you see more and more differences of squares helping you operate. And like I said, if you're not sure, you might as well rewrite something. So much of algebra is either substitution or manipulation. Those two things will get you very, very far. But sometimes manipulation means understanding the structure. Here we have squares and we go, okay, we can manipulate a difference of squares. And then the more practice you get, the more you will look at things like this and think, oh, those are all the terms in a perfect square trinomial. I've seen that before, so let's repackage and rewrite it that way. And then we have more differences of squares, and this time it's easier to see, right? The hardest part was getting started. This is easier to see, and now everything is written kind of like a sum of A, B, and C with some minus signs thrown in, and that's just the perimeter. We could have made a previous substitution. We could have at this point in time right here. In this line, we could have said, oh, that's the perimeter times the perimeter minus 2c, oops, not 2s, 2c, perimeter minus 2b, perimeter minus 2a, all over 2b. And then we would have said, okay, perimeter is 2s, and that'll help us, that'll help us get rid of fractions when we're done. Yeah, give this a try. Try to walk through these steps on your own. Try to teach it to somebody. When you can teach it to somebody else, that's when you really, really own it. Okay. This is going to be our last lesson for the week. And unfortunately, we don't have time to get through all of it, but we're going to get through some really important stuff here. Let's talk about what centers of triangles are. Now, it turns out that if we take any old triangle, we can drop the altitudes, and it just so happens that for every single possible triangle, they meet at a point. Do you know what we call that point?
The centroid.
That one's not the centroid. This one is the orthocenter. By the way, have you heard of an orthodontist?
Yeah, I use one.
Your teeth are perpendicular to the top and bottom of your mouth. Ortho means perpendicular.
Wow.
Another thing that we can do is take the perpendicular bisectors of each side. We find the midpoints of each side. And draw perpendicularly those perpendicular bisectors also seemingly magically intersect in one point. By the way, we call this concurrency. We say that those three lines are concurrent. If you draw two of them and you find their point of intersection, the third line has to go through that. It's amazing. It can't go a little to the right or a little to the left. It just goes boom, right through that one point. We call this point O, which is the circumcenter. And the reason this is the circumcenter is because if we were to draw the one circle that goes through the three vertices of that original triangle, its center is O. Next, if we take the same triangle, and forgive my terrible art, if we take the same triangle and we draw the angle bisectors, those also just kind of magically meet at a point. And this one is I. It is the incenter, meaning the center of the incircle of the triangle. By the way, it's hard to tell in this diagram, but the points of tangency are not necessarily on the angle bisectors. In fact, they're usually not. So be careful with that. Your drawings, when you have to have both those points of intersection and the point at which the angle bisector hits the opposite side, what you're going to find is that you need bigger drawings with finer points. in order to make sure that you don't see that wrong. So we've got Incenter, Orthocenter, Circumcenter, and earlier somebody mentioned our fourth one. If we identify the midpoints, and we draw the medians. The median connects a vertex with the opposite midpoint. Oh, I shouldn't have done this in red. I'll make this point right here. I'll make it G in black. G is the centroid. So let's talk about these letters for a second, because when you're first getting into this depth of geometry, these are tough to remember. O is the easiest, right? O is the circumcenter because O looks like a circle. So, okay, that's the easiest one. And the incenter, well, that's the center of a circle too, but we just go with I because that's the first letter in incenter. And then when we get to orthocenter, we go, oh, we already used O. We already used O, and we want a traditional variable so that it always represents, or usually represents, an orthocenter. So we wind up picking H. I don't know, because H is a letter with right angles, I think. And then centroid, we pick G because this is cool. The centroid of a triangle is its center of gravity. If you were to take a piece of cardboard, draw a triangle, draw out the medians, cut out the triangle, and then balance that triangle on the head of a pin, it's going to balance so long as the head of that pin is right on the centroid. So it's the center of gravity. So G is for gravity. Another thing that I've seen done is if you were to take that cardboard triangle and take 3 pieces of yarn, and on the end of each piece of yarn, put a ball, same size, same weight. Pick something that has a little bit of weight to it, but put a ball on the end of each yarn, and then tie the ends without the ball, all 3 of those ends together at one place, and then thread it such that you have like a little divot here at the vertices of the triangle, and let the ball hang down from those divots. What will happen is where the strings meet will move to the centroid. So these are our centers of triangles, and we're going to begin studying these, at least a little bit. The one that we're going to start with is the circumcenter. But before we get there, we're going to talk about if and only if theorems. And in logic, the way that we write this is we have some statement A, it implies some statement B, and then we have some statement B that implies some statement A. And this means that these 2 statements imply each other. If one of them is true, the other one is necessarily true. If one of them is false, then the other one is necessarily false. Okay? Well, let's talk about a common problem in geometry. Let's say that we have 2 points, and let's call them point A and point B. These are not the logic statements above, that's completely separate. Let's say we have points A and point B, and I ask, what is the locus of points equidistant from A and B?
That will be the line perpendicular to the line AB, which passes through the middle of AB.
Okay, that's a claim. Wow, what a spectacular claim. Okay, I like it. How do we prove that?
we could draw a circle using the points at which the perpendicular bisector passes through AB as our center.
Okay. We're gonna use the logic above. We don't need to bring circles into this. We're gonna use more triangle math here. Let's say that we have two statements. Statement 1 and statement 2. And we want to prove that these are equivalent statements. And we imagine some point C that is in this locus. And remember, locus is just a set of points. And what we want to say is if, or we want two statements. We want statement 1 to be C is on the perpendicular bisector of AB. And statement 2, AC is equal to BC. Right? Because statement B is the locus, right? And statement 1 is the description of it's the solution to the locus problem. So we want to prove that statement 1 implies statement 2 and that statement 2 implies statement 1. So let's start with statement 1 implies statement 2. So let's say that we have these points A and B, and we draw their perpendicular bisector. So those lengths are equal. And we say, hey, C is some point anywhere on this perpendicular bisector. Well, you know what? If it's the midpoint of AB, we're already done, because by definition, AC equals BC. But for any other point, what can we do with this diagram? We want to prove that AC equals BC. What do we see?
We form an isosceles triangle.
Yes, and I'm going to label that midpoint M. We have an isosceles triangle. Well, no. We don't know that yet, actually. We want to prove that AC equals BC. That's not what we're taking for granted. We're saying that we're saying that statement 1 is true, and we're trying to prove statement 2. But look at this diagram. What do we see that we've seen before?
Congruent triangles.
Yes, we have congruent triangles. CM is equal to itself. And now we have side, angle, side congruence. Okay, since these triangles are congruent, all of their sides are pairwise congruent to each other. Therefore, statement 2 is true. AC equals BC. Okay, so we proved that statement 2 implies statement 1. Sorry, we proved that statement 1 implies statement 2, and now we want to prove that statement 2 implies statement 1. So we're going to start with the same diagram. But this time, we don't know if we have a perpendicular bisector yet. What we know is that we have some other point C out here. And of course, if C is on the midpoint of AB, well, that's easy. That's already on the perpendicular bisector. But we have some point C. out here in space, out here in the plane, and we have equal distances. What can we do with this diagram?
If their sides are equal, their angles too are equal, so it's an isosceles triangle.
You can see we have some equal angles.
Well, that means that the altitude would touch the middle of AB.
Okay. If we were to draw the altitude, and I'm going to go ahead and disallow just saying that angles A and B are equal to each other, mostly because I want this to rest on a more fundamental basis, right? That really comes from what we're about to do. But what we're about to do is the same thing that told us the angles were the same. Now, if we draw this right here, now we have side-side angle, which is not a congruence theorem. We're going to do something different. Instead of drawing the altitude, we're going to draw to the midpoint. Now, if we draw to the midpoint, that means that this is the same as this, but what else is true?
They share a side.
That these two triangles are congruent.
By what congruence theorem?
Side, side, side.
Yeah. And since they are congruent, we have equal angles that make up a straight angle, and we divide each by 2 to get a 90-degree angle. Therefore, C, which is on line CM, is on the perpendicular bisector of AB. And statement 2 does imply statement 1. So statement 1 implies statement 2. Statement 2 implies statement 1, so they are equivalent statements. And this is really, really important because we're going to use these in a kind of spectacular way, right? Statement 1 does not read the same as statement 2. These are very different observations that we might make while working on a geometry problem. But when one of them is true, it automatically means that the other one is true. So let's see, what does that mean for us? Okay, we're going to go on the Circumcenter adventure. Now let's say that we've got a triangle ABC, any old triangle. And previously we asked, what is the locus of points equidistant from 2 points in a plane? Well, kind of a natural next step is to ask, what is the locus of points equidistant from 3 points in a plane? And that's a tough question to answer quite so directly. Tuition makes that tougher, intuition. Well, we can go 2 pairs at a time. We can ask, what is the locus of points equidistant from A and B? And we know that those are the points on the perpendicular bisector of AB. I'll call that L. Okay. So now we say, okay, what are the points that are equidistant from A and C? Those are the points on this line, which I'm going to call M. Okay, so these intersect at a point, and I've not drawn this well, so I'm going to redraw just a little bit. Forgive me. Pretend that these are perpendicular bisectors. I'm not the best geometric artist. So the points that are equidistant from B and C are also on a perpendicular bisector. But here's the thing. I want to understand why this line, the third line that we can draw, the third perpendicular bisector, does or does not go through this point. I'm going to go ahead and label this point O. That's where L and M meet. And what do we know about the points that pass through O?
We know that the line L is all the points on line L are equidistant from A and B, and that all the points on I'm not sure what that other letter is, but all the points on that line are also equidistant from A and C. So if all the points on the first line are equidistant from A and B, and on the second one are equidistant from A and C, wherever they meet would be equidistant from A, B, and C.
Okay, we know that O is on the perpendicular bisector of AB, and O is on the perpendicular bisector of AC. Any point on the perpendicular bisector of AB is equidistant from A and B. Any point on the perpendicular bisector of AC is equidistant from A and C. Now notice, these two statements up here at the top, we are using that statement 1 implies statement 2. This is a statement 1 implies statement 2, both of these. But now we know that OA equals OB and OA equals OC. Therefore, what must also be true?
OA equals OB.
Say that again.
OB equals OC, sorry.
OB equals OC by transitivity. And now, since OB equals OC, what do we know?
O is equidistant from points A, B, and C.
Well, that's true. But think about statement 1 and statement 2. If OB is equal to OC, then
O must be the perpendicular bisector of BC.
O is on the perpendicular bisector of BC. And that's statement 2 implies statement 1. This is why this, two-directional logic, these equivalent statements are so important. We use statement 1 implies statement 2 twice. Then we used that information through transitivity to set up the use of statement 2 to imply statement 1. What this means is, since we could see that OA was equal to OB, and OA was equal to OC, so OB was equal to OC, therefore, O is on the perpendicular bisector of BC. So the perpendicular bisector BC, it can't miss O. It has to go through that same point of intersection. So we just proved the existence of the circumcenter. We proved that with every triangle, those perpendicular bisectors go through the same point. And it was because of the magic of that if and only if theorem. So yeah, very, very cool point. And I'm going to draw that circle. OA, OB, and OC are all the radius. And by the way, that helps us with constructions. How do we construct a perpendicular bisector?
A perpendicular bisector is constructed by placing the pointed end on either A or B, and then opening a certain degree and drawing a curve. Then you leave it as open to that same degree and shift to the other points and draw a curve that will intersect with the already drawn curve, and that's a perpendicular bisector.
Yeah, we connect the points of intersection, which are each equidistant from A and B, because we've kept those radii the same. So we have multiple points that are, we have all the points that are equidistant from A and B. That gives us the perpendicular bisector. Okay, good. And if you can draw those perpendicular bisectors, you can now always construct the center of the circumcircle. Okay, we're going to do something similar now with angle bisectors. We're going to prove the existence of the incenter of a triangle. And in order to do that, we are once again going to create an if and only if theorem using a locus problem. Let's say that we have a ray, two rays. And we want to know the locus of points that are equidistant from those two rays. Points like that and that.
Then that's the angle bisector, all points on the angle bisector.
So we have a conjecture. So the conjecture is that this locus is the angle bisector, the points on the angle bisector. And if we have a point C right here, call this point P, and B, and A are points on those rays. So we could say okay, so let's prove that statement 1 implies statement 2 first. So if C is on the angle bisector, so we start with the information. Those angles are the same. And we have some point C. And we drop a perpendicular, and we drop a perpendicular. Well, what do we have?
We form two.
Congruent triangles.
Yeah, we have congruent triangles. We have two angles and a side. So by AAS congruence, we have PCX is the same as PCY. And because of that, we have that is the same as that. So C is equidistant from the two lines. That's the perpendicular distance, which we already proved today was the shortest distance from a point to a line. Okay, so statement 2 implies statement 1. Now let's try to prove that. Sorry, statement 1 implies statement 2. Now we're going to prove that statement 2 implies statement 1. This time, we're not going to assume it's on the angle bisector. We're going to say that distance is the same as. Somebody please silence, non-orally. Can you silence your microphone? Thank you. So we'll say the foot of that perpendicular is y, this one x, this one p. And now we will draw into this diagram. We'll connect P to C. Our goal is to prove this is an angle bisector, but we don't know yet. But what do we have in our diagram?
We form more congruent triangles by SAS congruence.
It's not SAS congruence. What congruence theorem are we using?
Sorry, it's ASS congruence.
There is no ASS congruence, but there is a special case of SSA. And you know what? This is the one that we didn't prove. We didn't prove HL congruence or similarity, but know that it works. And part of the reason, we could say the reason HL works is because using the Pythagorean theorem, we can always get the third side from the first two. Then we have those third sides that are the same, and SSS finishes the job for us. So by HL congruence, triangle PCY is congruent to triangle PCX. And because those triangles are congruent, corresponding parts are congruent. So statement 2 did imply statement 1. C is indeed on the angle bisector APB. So we have equivalent statements. Once again, we have an if and only if theorem. We say that that a point is equidistant from two rays if and only if it is on their angle bisector. And now how does that help us with the incenter? So once again, we'll start with an arbitrary triangle, any old triangle. And once again, we're going to start with two rays. We're going to start with two lines. We can go past the point if we want. And we will say they meet at a point, we'll call it I. And we ask, what do we know about this point I? Well, it's on angle bisector. Angle bisector at A. And statement 1 implies statement 2. So something that is on the angle bisector is therefore equidistant from line AB and line AC. I'm going to draw those perpendicular distances. And I didn't draw things well enough. They don't look the same, but they are the same. Okay. And then we're going to use statement 1 implies statement 2 again. I is on the angle bisector of B. Therefore, I is equidistant from AB, line AB, and line BC. So that right there is the same as the second one of those that I drew. So I'm gonna throw out 3 little variables over here. I'll call this X, Y, and Z. Those links. First time around we said X equals Y. The second time around we said Y equals Z. So by transitivity, what do we know?
X equals Z.
Okay, good. So we know that point I is equidistant from AC and BC. And that allows us to say, hey, statement 2 implies statement 1. If this point is equidistant from those 2 lines, then it must lie on the angle bisector at C. So those 3 lines cannot miss. They must be concurrent. That third one does go through the point of intersection between the first 2 of those angle bisectors. Are there any questions or thoughts about this? All those distances are equal, so we can sketch this. We'll call it a circle. Pretend for me. Be charitable. Okay, so I'll go ahead and say this. These are the 2 easier of the proofs of the existences of these centers. We're going to go through one more right here. We could do some problem solving. We can practice this, but I'm sure you can find many, many practice problems over time that involve what we've just gone through. On the other hand, the proof of the existence of the orthocenter is a really, really fun proof. And I want all of you to see it. Actually, draw this a little bit smaller. You will soon see why. Okay, let's go back to one of the most basic things that we did over the past 3 weeks of geometry. We learned that we can get free information in a diagram when we draw a line through a point parallel to another line that point is not on in the plane. Sorry, I didn't say that well. Before we do that though, let's take a look at something. Let's take a look at these altitudes. And we may say, hey, it kind of looks like they go through the same point, but we can't make that assumption. So we start looking for ways to generate information. We want free information. I'll tell you this, the first time I was asked if I could prove the existence of the Orthocenter, I started using the Pythagorean Theorem. I threw variables all over this diagram. I had no idea what I was doing. I had a mess of equations and 3 pages of algebra, and it went nowhere. But here's what we can do to get more information. We get free information by drawing a line through A parallel to BC. What free information do we get? Well, we get that that angle is equal to that angle, and that angle is the same as that angle. Okay, that's some free information, sure. Well, you know, if something works for us once, sometimes we just ought to see what happens when we do it again. So I'm going to draw a line through C parallel to AB. And from that we get, well, that angle is equal to our original angle B, and this angle right here is equal to our original angle A. Okay? Well, let's just keep on doing the same thing. And this is our original angle C, and this is our original angle A. What do we have here?
Well, this could be used as a proof that the sum of the angles in a triangle, but we've also created other angles, other triangles.
We have created other triangles. What's true about those triangles?
I think all 4 triangles are similar.
Ah, that's a good observation. We can do even better than that. They are all similar.
We could label each angle, since we know that these two angles are going to be same. Like for example, on angle B, we see that there's an angle there and an angle C. So then we can find out angle X, which would be A.
Okay, we can label all the angles. We do have similar triangles, but we have something even better.
Congruent triangles?
Congruent triangles, right. Each one of those outer triangles shares one side with the original triangle. So all 4 of them are congruent, and they are all similar to the big triangle with a similarity ratio of 2 to 1. Okay,
yeah.
This is nice. We have all these congruent triangles. And by the way, we call these triangles medial triangles. If I were to just draw any old triangle, and I were to connect the midpoints. Oh, by the way, I didn't say we had midpoints, did I? If these are congruent triangles, take a look at this. This original side is here and here. Then this original side is here and here. This original side length is here and here. So A, B, and C are the midpoints of YZ, ZX, and XY. And if we were to identify the midpoints of a triangle and connect them, we will always get congruent triangles and we will always have that 1-to-2 ratio between the triangle in the middle and the big triangle. And we call this, we could call the triangle in the middle the inner medial triangle of the original triangle, or we could say the original triangle is the outer medial triangle relative to the inner triangle. And the area ratio is 1-to-4. Okay, so that's kind of an aside right there. We don't really need to talk about this in order to talk about the problem that we're working on, but it's nice to know words. So back to this picture right here. Let's recap what we've done so far. We started out looking at altitudes, but we weren't sure what we could do. So we drew lines through each point parallel to the original sides. Then boom, we had all this new angle information. And from all that new angle information, we were able to identify congruent triangles around this diagram. And because of those congruent triangles, we realized that A is the midpoint of YZ, B is the midpoint of ZX, and C is the midpoint of XY. Now I want you to look at those original green lines and tell me what they are.
They are the midpoints of the bigger lines. Like C is the midpoint of line XY, and B is the midpoint of line ZX, and A is the midpoint of line ZY.
Okay, good. You're almost there, non-gnarly. These green lines pass through the midpoints of the sides of triangle XYZ. Not only do they pass through the midpoint, so they are bisectors. What else is true?
Perpendicular bisector.
They are perpendicular bisectors, Salorm. How do we know for sure? I mean, we have this right angle right here. How do we know it's a right angle at A also?
Well, AC is parallel to ZX, and the angle that's formed is 90 degrees. So the angle must be 90 degrees.
Right. If this blue angle is true and this line is parallel to this one, then we have alternate interior angles, and that is also perpendicular. Same with right here and right there. Same with right here and right there. So the three green lines are the perpendicular bisectors of X, Y, and Z, and we have already proved today that the perpendicular bisectors are concurrent. They are concurrent at the circumcenter of the big triangle. And that also happens to be the orthocenter of the small triangle, because we started assuming that those were the altitudes of the original triangle. So since the circumcenter of the big triangle exists, the orthocenter of the original smaller triangle exists, and the altitudes do necessarily pass through one point. Any questions or thoughts about this proof?
So can this proof be used as a proof for the circumcenter as well?
No, we relied on knowledge of the circumcenter. And if we said, hey, we're going to use the circumcenter to prove the existence of the orthocenter, and then try to use the existence of the orthocenter to prove the circumcenter, that would be circular logic. It would be like taking two ghosts and saying, if the first ghost exists, then the second one exists. And if the second one exists, then the first one exists. But that doesn't tell you that the two ghosts exist. But we have an easier fundamental path toward proving the existence of the circumcenter. So we might as well take the path toward engineering that, toward establishing that, and then using that fact to establish the orthocenter. It can be done in other ways, but this is more commonly foundational. Okay. Now let's take a look at the circumcenter of a right triangle. Let's say that we've got a 6, 8, 10 right triangle. And I'm going to draw in the perpendicular bisectors. And I'll go ahead and draw perpendicular to the legs. Oh my gosh. Is that on the, is that point of intersection right on the hypotenuse?
I think so.
Wow. Is that a coincidence?
Maybe.
I remember seeing this in the AOPS book. It's not a coincidence, and then you go on to.
Do you remember what we do, Salam?
My notes in a different book.
That's okay. Let's talk about what happens here. Now notice that we've drawn a rectangle in this diagram. Notice that triangle AYO is similar to ACB. How do we know that?
Because the parallel lines give us reason to believe that the angles are correspondent.
Yeah, the parallel lines gave us right angles. Okay, what is the similarity ratio?
I think it's yeah.
1 to 2. Okay, so AO then over AB is 1/2. AO is half the hypotenuse. Okay, similarly, we could show that OZB is similar to triangle ACB, and we have a ratio of similarity of 1/2 also. So BO over AB is 1/2. Okay, huh.
Mr. Crawford,
Yes.
could you mark OZ to be the same length as AY? Or
Yeah, we have a rectangle, so YC is equal to OZ. So here's what I'm going to say. We're going to have the same result. Suppose that instead of O, we picked a point M that was the midpoint of AB. Then we would have AY over AC equals AM over AB. And they would share an angle. Therefore, triangles AYC and A, M, B are similar. What did we learn?
Mr. Crawford, please, I think you wrote AYC instead of AYM.
Thank you. You're right. And the second one is ACB. Thanks for picking up on that. So what is this? What did we learn here?
It's the radius, if we were to draw the circle, the radius would be AO and OB.
Well, in particular, we just learned that O is M. How do we learn that O is M?
Because AO is the same distance as OB, which means that the midpoint has to be O, which is the same as M.
Well, we learned that M is on the perpendicular bisector of AC, and M is on the perpendicular bisector of BC. So it must be the same as that point O. So the midpoint of the hypotenuse is the circumcenter of the right triangle. And if we draw that circle, there we go. Midpoint of the diameter is the hypotenuse. And in fact, this is something kind of cool, which is if we draw any diameter like this and we start drawing inscribed angles whose endpoints are along that diameter, we get this cascade of right angles.
Yeah, I think we did this with Wendy the last time.
Oh, have you done this before?
Yeah.
Okay. Okay, now here's a question. How many points define a circle?
I want to say 2, but I'm not sure exactly what you mean by points that define a circle.
Well, 2 points define a line, because if I have just 1 point, I can draw infinitely many lines in the plane through that point. But if I draw 2 points in a plane, there is exactly 1 line that passes through those 2 points. Now in space, there would be infinitely many planes that pass through those 2 points. But a third point, somewhere off that line, there would only be 1 plane that would pass through all 3 of those points. So 2 points define a line in a plane, 3 points define a plane in space. When I say define, I mean that there is one and only one figure that satisfies that information. So, is 1 point good enough to define a circle?
No, because I think 2 points define the diameter of a circle.
No, I think it's 3. 3 points define a circle.
Well, 1 is definitely too few because I can draw a whole bunch of circles that pass through that 1 point. If I have 2 points, well, non-Norley says diameter, but I can still draw other circles through those 2 points.
Yes, I think it's 3.
Can you prove it?
It will be kind of like the circumcenter of a triangle.
Yes. Yeah, the perpendicular bisectors can only meet at 1 point, and that 1 point has a fixed distance giving us one possible circle, and that's it. So what we say is a 4th point means that either we have no circle or a 4th point would have to be on the same circle, at which point we would say that it overdefines the circle. And it's fine to overdefine something. Sometimes we do. And in that case, we would have a total of 4 different possible triangles that we could draw, all of which have the same circumcenter and same circumcircle. Okay? I apologize. I'm going to find one good last problem to end the week with here. Oh, there's one more theorem that I know that I want to walk through with all of you.
Mr. Crawford.
Yes.
In our previous lesson, you said that you would ask Mr. Joel whether we could continue our lessons after summer.
Yeah, I'm going to work that out with Joel later.
Okay.
So let's say that we have a triangle here. By the way, people are dropping out, but we have one more problem to go through. We've got this triangle right here. Let's draw the medians. And they pass through the centroid. And let's think about what we know about the areas. We'll say this is D, E, and F. Remember that same base, same height principle?
Yeah.
Yeah.
Can somebody tell me 2 triangles that have the same area?
Triangle ADB and triangle ADC.
Yes. What's another pair of triangles that have the same area?
Triangle BGD and triangle DGC.
Good. And you know what? With these 2 smaller triangles, I'm going to throw down variables. I'm going to say X is the area of this triangle, and therefore X must be the area of that triangle. That's BGD and CGD. Now here's what I want you to do. Tilt your brains. Do the same thing again. Here, we used BC. It's easier to see that visually. We used BC as equal bases, or we broke it up into equal bases of 2 triangles. We did that in 2 different ways. But I want you to tilt your brain and do that with a different side.
So that means that the area of triangle AGE would be equal to that of CGE.
That's true, and I'm going to call both of those y.
So it'd be similar. So triangle AGF would be the same as triangle FGB.
They're not the same, but they do have the same areas.
Oh, my bad.
Let's be careful with language. They're not congruent. They're not similar. They have the same bases, and they have the same heights to those bases. Okay, so we have we've divided this triangle up into 6 different areas. But you know what we haven't used yet was the very first triangle. I can't remember who mentioned that one first, but let's take a look at those equal areas in terms of these variables. Well, one of those triangles has area x plus 2z, and the other one has area x plus 2y. What does that tell us?
That Z and Y are equal.
Yeah, z and y are the same. And once again, we can tilt our heads and do something similar and use big triangles. We can say, hey, triangle BAE has the same area as triangle BCE. And that would give us y plus 2z equals y plus 2x. And that tells us z equals x. And now we have x equals y equals z. And what did we just prove?
That each of the triangles formed by the different medians are equal.
What do you mean are equal?
Have equal area, sorry.
Have equal areas, that's right. The medians divide a triangle into 6 equal areas. They're not congruent. They might be. In an equilateral triangle, they will be. But they have equal areas. They're not necessarily congruent. They're not necessarily similar. And I want to point something out. The one center of a circle that we didn't prove the existence of today falls out of some of this work. And I think that's in AOPS Volume 1. I can't remember for sure. But try to see if you can use, this diagram to prove the existence of the centroid. But I'm going to point something out now. We just proved that all these areas are equal. And I want us to focus in on one of those triangles for a moment. Let's see. Let's use this one right here, ABE. Now imagine for a moment that we're looking along this line for the bases. So we've got this base and this base. Somebody tell me, what is the ratio of the areas of A, B, E, and A, G, E?
Um, 2:1.
Isn't it 1-to-1 since we just proved that they're all equal?
We proved that the 6 little triangles all have
Are
equal.
equal. Yeah, and there are 2 of those on one side and 1 on the other. So it's be 2:1.
It's not 2-to-1.
It's 1-to-1 because 3x is to 3x.
Okay, it's 3x on top. And the area of AGE is just x.
Oh,
Yeah.
sorry, I didn't see the other. Okay, sorry, my bad. Yeah, it's 3:1 rather.
Yeah.
So this median to this piece is 3-to-1. So the larger piece of the median to the smaller piece of the median, we'd say those lengths are like 2A and A. The centroid breaks up each median into 2-to-1 ratio pieces. And it's because of these little equal areas that we can say that. And it's using that same height to the base principle that we can compare the areas in order to compare the lengths. So we've proved that the medians of a triangle divide each other into 2-to-1 ratios. And that's probably a fact that most of you knew before. Okay, here's what I'm going to say. Find the appropriate chapters. I don't have what I usually have, which is dozens and dozens of pages of material and problems and whatnot. So I'm going to say find the chapters in Art of Problem Solving Volume 1 that have this geometry and practice some of the problems from there. And I will see you on Friday after your last exam.
If I recall,
Can I ask a question?
Sorry, question? I had two people at once. So Lorm, go ahead.
I was just trying to remember, and I think it was on the first chapter that this was on, the centroid, the orthocenter, and all the different centers that you can form triangles. So I just wanted everybody to know.
Okay. Did somebody else have a question or a thought?
Yeah, I had a question. So after our last exam, how are things going to play out? What are we going to do next? Like, what would be the how would things continue?
Well, this is the last week of the program. You'll take your last exam tomorrow, and then on Friday we'll meet for office hours again, and that'll be our last meeting.
On the schedule, Mr. Joel sent, it said that we had a meeting after this week, post-test meeting.
Oh, I did not realize that on the schedule. Like an end of camp meeting.
Yeah.
Okay. Thank you for mentioning that. I don't think I had it on my own calendar yet. But I guess I'll see you then once after Friday. Any other questions or thoughts? Okay. See you all on Friday.
Okay, thank you.
Bye.
Bye.